All right, hello everyone. Welcome to another episode of History of Science and Technology Q&A. Let's see, we had a few questions saved up, but not so many. So I'm looking forward to questions about anything about history of science and technology, either things that you might think I've been personally involved in or things from longer ago. You know, I have to tell you, I just spent the last couple of hours doing something very seemingly un-CEO-like, debugging a piece of code that, along with a lot of other people, that is something which I've been complaining about for like 3 years, that there's a particular failure that's happening when I do large-scale parallel computations across hundreds of machines and so on. And it's like the occasional failures, and it's like, what's going on? It is an interesting process, debugging code, and maybe we could talk a little bit about the history of bugs and why bugs happen and so on. I think the thing, and maybe some of my experiences of this, I think that the name bug originally comes from, I think it was the ENIAC in the late 1940s, maybe, early electronic computer, where some failure happened, and it turned out there was a big machine that filled the whole room, and it turned out the failure was a hardware failure, and the cause of the failure was a moth that got into the machine, and that was a bug in the machine, so to speak, and hence the name bug for some kind of error. But of course, that was a hardware error. What we're now dealing with mostly are software errors. I have to say, back in the day, there used to be, I don't know, 40 years ago or something, used to be much more common for sort of hardware errors to be the things that one thought about in terms of machines. I remember a VAX 11780 was a so-called mini computer, which meant that it wasn't the size of a whole room, it was only the size of a few giant file cabinets, well, many giant file cabinets. I remember that it used to have these interrupt levels. You know, when machines run, they are trying to, there are different processes are trying to run, and the CPU the operating system is deciding which process to run, and there can be these interrupt levels where some other thing can interrupt what's happening, and the thing of higher interrupt priority level will get to run next. Maybe it's something that comes in from input output or some such other thing. I do remember on the VAX that there was I think it was a level 13 priority interrupt, and the description of it was the machine is on fire. And that was and of course the goal was, if the machine detected that it was on fire, the most high priority thing is to go shut down disks, retract heads from these spinning disks, things like that. Because in those days, when one talked about a disk, I mean, I remember when we got these maybe a couple of megabyte disks, these were big things the size of a washing machine, and they're big physical platters that were spinning, big things that were like 3 feet across or something or more, that were spinning around. Usually disks, I think, have always spun at about 60 hertz. I think that's always the speed that they spin at, but the amount of angular momentum in something that is a very big, 3-foot piece of metal is quite something. But anyway, the question of so we're talking about kind of the origin of bugs. So, the very first, what one can see is the very first kind of proto-program that anybody wrote was what Alan Turing wrote when he wrote his original paper in 1936 that originated the idea of the universal Turing machine. The idea of the universal Turing machine being, we can write down this kind of idealization of how a mechanical process for doing a mathematical computation might work. And we can show that this particular kind of hardware process is capable of emulating any other Turing machine of the same type. That was kind of Alan Turing's original proof. It's a kind of hard to read paper, not least because the notation is quite, he's inventing a notation for a new area that didn't really have notation before. He uses Greek letters for some things, and as he put it in 1936, German letters, which means Gothic type, for other kinds of things. And he gives kind of a program for his universal Turing machine, And that program was riddled with bugs. He didn't have any idea that that was sort of a thing that, you would write a program and you would imagine this is a program that's going to run, but you wouldn't know to think, oh, I might have made a mistake. And I suppose in the best model for that type of thing would be theorem proving in mathematics. You write the proof of a theorem. Did you make any mistake or not? Well, I'm quite certain that the literature of mathematics and many famous proofs are, if you really micro look at them, will have bugs in them. But you don't know that because the consumers of those proofs are just mere humans who are just going to read them and say, oh, that's okay, it's all good. I think that the thing that, but if you have a computer run that code, the computer is much less forgiving and it will notice that there's a bug. When it comes to sort of written documents and things, there's a question about bugs in, for example, legal documents. A famous story, which I believe to be a true story, is when Kurt Gödel was going to do his citizenship interview in Princeton, well, I think in Trenton, New Jersey. He was a friend of Albert Einstein's, and the two of them were going off together for Kurt Gödel to go and do his US citizenship interview. And Kurt Gödel was noticing that he'd read, because he was going to get quizzed on things about the US Constitution, he'd read the US Constitution very carefully, and it had a bug. It was possible for the US to become a dictatorship if this and this and this happened, and this person died, and this person, whatever. I don't know exactly what the chain of events was. Einstein convinced him not to bring that up. Obviously, Kurt Gödel was at the time coming from well, I guess he'd grown up in Austria, but at that point, yeah, he must have been in Vienna at that point. He'd come from Austria, which had been taken over by Germany at that point. In any case, the thing that we're talking about bugs, and there's kind of a long history of people not really expecting bugs. That was something which came up, it snuck up slowly on people as programs got more complicated and as people kind of got to the point where routinely there would be very big programs. And I think I'm trying to think about other cases, like for example, von Neumann, I think, had stated in the probably the beginning of the 1950s, no program that anybody would ever seriously want to write will be more than, I forget, 200, 400 lines long, something like this. That was an interesting mistake. It was a mistake that I think came from a failure to understand modularity in code, failure to understand that you could have a sub-function that you could separately write. And that might be, von Neumann would not be entirely wrong that by the time you have a single function that's more than a few hundred lines long, there's probably something horribly wrong happening. It's going to be very hard to understand what's going on, because we humans tend to sort of like to have bite-sized things to think about. We like to have kind of, this is a function that does this. It's being called by some function that does this and this, but we want each sort of piece as a sort of cognitive element that's comparatively small. And so I think that was the thing that that was sort of the cause of that mistake, was that a sort of a single proof in mathematics probably wouldn't be longer than that. But there might be, in a sense, sub-lemmas that might go off to other papers and things, and von Neumann didn't really think of that idea in terms of what computers might do. I'm not quite sure who invented the notion of being able to call a sub-function, because in order to do that, you have to have the notion of a stack, for example, and I'm not sure when that notion came into being. I'm trying to think whether the first computer that I used didn't explicitly have a stack, I think. I think that was something that got created later on. I mean, in actual computers, like in a Unix operating system, for instance, the memory of the heap memory of just sort of working memory, it grows in memory locations sort of up from the bottom of address space, and the stack, which stores the information about how to return from a function call, that grows from the bottom of, from the top of memory space. And back in the day, I don't know if it's still true, the disaster that could happen would be you'd use so much stack space and so much heap space, eventually those addresses meet in the middle, and then that process is toast. But in any case, this whole question of how programs, how one thinks about bugs in programs and kind of almost a calculus of bugs, I think we still don't have a good calculus of bugs. It's still the case that for example, if we look at human medical diagnosis, there's a well-classified collection of kinds of things that can go wrong with us humans. There's no similar thing for bugs in programs. And it's an anecdotal thing as you do more programming that you learn different kinds of things that go wrong. What about the end case? Is there an off by one error? Could you be writing outside of this area of memory? Things like that. Lots of modern systems, certainly in Wolfram language, for example, the kind of scribbling on memory is something that can't be done but at the user level, and lots of modern programming languages have various kinds of protections against that. But that's just one of a sort of infinite number of possible bugs. The bug that we were just looking at is a bug that is deep inside inter-process communication, and it was, well, I could describe what was happening, but I think we just found it actually. And it's a bug in oh gosh, I mean, it was a bug where you're launching 150 different subprocessors, and out of those, on one machine, the machine only produces 11 out of the 12 processors that it should be launching. And sometimes it's a different number. If you ask the machine to launch 60 processors, it will be some random collection of 3 processors that won't launch. Those processors that don't launch because, oh boy, we're going to get super technical here, because they are, well, they're being connected to through SSH, the secure shell, and then the secure shell, the process is calling back to its parent through the secure shell, and somehow it's ending up in some kind of wait state as it tries to call back to the parent, and it's burning, it's just looping in the CPU. Actually, it's looping partly in user space and partly in system space, more in system space than user space. And anyway, bottom line, it's probably some bug in handling an edge case of when something just almost hit some timeout and some deep inside some piece of code. But in any case, I mean, I could also talk a little bit about famous bugs. I mean, it used to be the case that there was a kind of a news group, alt.risks or something, I forget, that kind of listed some of the well-known bugs that have happened in the history of technology and particularly computing and software. I mean, a famous one, there was a missile, an anti-shell missile thing that had a famous bug where it was, it had a counter that was some kind of timing counter, and that timing counter was overran. So it was a timing counter that was like, I don't know, 32, maybe probably in those days, 16-bit counter. It was counting up every second. And if the system was turned on for too long, then it would end up, the numbers, it didn't have any protection for whether that number got too big to store in a 16-bit integer, and so it wrapped around, and then all bets were off and it did the wrong thing. But there are so many of these stories. There are a lot of stories of things where there was something that was a number, for example, stored in a fixed size register, and that register, the number got too big. That's a pretty common story. And there are a bunch of these. I mean, I could rattle off a few others, but they're things where it's one general category of bug is the person just didn't think of that corner case. They didn't sort of think about all the possible things that could happen. And as one tries to sort of verify programs, sometimes one is able to think about all the possible things that can happen. Sometimes, like the debugging we were just doing, which is a real-time program that involves communication between multiple machines and processes and timing information and so on, that's not something where you can expect in the normal way, at least to just say, run that code. For example, a very common kind of issue in code is coverage analysis. Like, is it in fact the case that you have a test that will actually go down every branch of this code? That's a hard thing to do when, for example, in debugging in quality assurance for Wolfram language, we're able to do a lot of that, but some pieces are hard to do because some pieces rely on things like real-time interrupts. Did the person press this button to stop things at this moment? How do you deal with that? Can you produce something which will have coverage for all of those sort of real-time conditions? Well, anyway, a little bit on that. There's a question here from Parmenides asking, did I ever meet Andrei Sakharov? What do I think of his cosmology? I did not meet Andrei Sakharov. He was he wrote some interesting papers about cosmology and about the origin of the discrepancy between matter and antimatter in the universe. As I recall, it's been a long time. Those papers must have been in the late 1960s, probably. And they were papers that will have been relevant to work that I was doing in the late 1970s. One of the big questions I was interested in back, when I was a kid, mid-1970s, was one knows about matter and antimatter, protons, antiprotons, electrons, positrons, and so on. Right around here, everything we're dealing with, the Earth, the sun, whatever, it's all made of matter. One would think from sort of the symmetry of things that there would be about as much antimatter in the universe as matter. And so how could that be, could that be the case? For example, as we look out at the Andromeda galaxy, could it be an anti-galaxy? Could it be made of antimatter? Where in the universe could there be matter versus antimatter? And I remember back in 1976, that was very much a question. And I remember trying to figure out if there were parts of the universe that were made of matter and other parts that were made of antimatter, there would be some region in between them where there would be annihilation of matter and antimatter. And one of the things that could happen is this Leidenfrost phenomenon, where kind of when things are kind of boiling and they're producing vapor, that's producing pressure that's holding apart these things that would otherwise be boiling, so to speak. And the same kind of thing would happen with matter and antimatter. Those things might be, let's say, gravitationally attracted to each other, but at the boundary where matter and antimatter are annihilating, lots of energy will be being produced, and that will produce radiation pressure, which will potentially hold the matter and antimatter apart. So I was interested in, could it be the case that there was antimatter galaxies in the universe, but there was just so little matter between galaxies in intergalactic space? There's maybe one hydrogen atom per cubic meter, for example. Was that sufficiently little that there just wouldn't be very much annihilation radiation, which would be visible in gamma ray astronomy and things like that? You should be able to see annihilation radiation if there was any. Would there be annihilation radiation that would reveal the fact that parts of the universe were made of matter and parts of antimatter? It's a big question. If you just see light from a star, how can you tell whether it's light from a star or from an anti-star? And it's a pretty subtle thing. There are some ways to tell using, essentially using circular polarization of light. And that happens because one of the features of turns out that charge conjugation, the symmetry from matter to antimatter, is not a perfect symmetry of the universe. It is violated by weak interactions. And one feature of it is a consequence for neutrinos, that a neutrino is always left-handed, always spins in such a way that its spin direction is sort of left-handed rule relative to its direction of motion. Antineutrinos are right-handed. If there was perfect charge conjugation symmetry, both neutrinos and antineutrinos would have sort of the same handedness, so the same handedness. So there's ways to potentially, I haven't looked at this in 40 years probably, there's ways that one can expect that in various kinds of nuclear beta decay, where neutrinos are involved, that there would be photons that would also be produced that would have different left and right circular polarization, and you might be able to detect that from stars and see whether, oh, in that supernova, was it a supernova or an anti-supernova? Anyway, the thing that, as I recall, was then a question. Well, it was a question I was interested in 1976 and so on. How could one understand the matter versus antimatter story for the universe? And I think it was an idea of Sakharov's, and other people were involved by this point, that if there was a violation of, if that, well, that you could get, let's see, I mean, I worked on this quite extensively. So the question was, in the very early universe, the interaction between the expansion of the universe and the small effects of charge conjugation violation, actually it had to be so-called CP violation, violation of charge conjugation and parity together, small CP violation effects in an expanding universe, where the expanding universe effectively has defined a time direction, that those effects could lead to a difference in the amount of matter and antimatter. And I seem to recall there were papers of Andrei Sakharov's from the 1960s about related kinds of things. And I think that the question that came out there was, it turns out, if you have a particle and an antiparticle, let's say I don't know, a kaon and an anti-kaon, they have the same lifetime. The total lifetime, total decay, the half-life of those particles is the same. But the partial decay rates of, let's say, I don't know, a K plus going to a pi plus and a pi zero versus a K plus bar, that's a K minus, going to a pi minus and a pi zero, those partial rates are allowed to be different according to CPT invariance, which is something we believe to be a general symmetry of quantum field theories. And that was, I mean, I can talk a little bit about the history. Gosh, there's lots of history, lots of interesting history there. About, well, we can talk about, let's talk about the history of antimatter for a minute. The antimatter, really quite an interesting history. Nobody imagined it would be there until 1930s, when Paul Dirac, a physicist in Cambridge, a very mathematically oriented physicist, was tried to figure out the so-called wave equation for a relativistic particle like an electron that was capable of going close to the speed of light. Prior to that, in the early days of quantum mechanics in the 1920s, this thing called the Schrödinger equation, which is the equation for the so-called wave function, essentially quantum amplitude of quantum mechanical stuff, which eventually the mod squared of it gives you probabilities according to the standard interpretation of quantum mechanics. That idea, so the Schrödinger equation was an equation good for non-relativistic particles. It's the thing that's used all the time today in studying lots of quantum effects in chemistry and elsewhere. But one wanted an equation which was consistent with relativity. The Schrödinger equation is an equation which has, it's like a diffusion equation. It's first order in time, first order time derivative, and it's second order in space. So it's not treating space and time kind of symmetrically there. And so the question was there a similar equation for relativistic particles? There was a thing called the Klein-Gordon equation, which was good for spin zero particles that were, and there was also an equation for the electromagnetic field, which is a spin one particle. But the real question was, what about electrons that were kind of spin half particles? What would be their relativistic wave equation? And that's what Paul Dirac worked out. He kind of had this idea, which is sort of a weird idea, that the differential operator that appears in the equations for spin zero and spin one and so on, you can take kind of the square root of that operator, and you get this kind of thing, which is a linear differential operator together with these so-called Dirac gamma matrices, and it's all a little bit complicated. But one feature of sort of taking the square root is that there was a positive square root. It's like when you take the square root of 1 or something, you get +1 and -1. And that's what happened in the Dirac equation. You got both the positive square root and the negative square root, so to speak. And then the question was, what did those negative square roots mean? Because they were things like an electron, but they were things that had negative energy. And so the question was, what would be the interpretation of that? Now, it was known by that point, the Pauli exclusion principle was known. That's the idea that when you have a spin-a-half particle, for example, you can't ever have two spin-a-half particles in exactly the same state. They will be excluded from being in the same state. That was a Wolfgang Pauli idea from the 1920s. And it was something where I think we actually slowly beginning to understand in our model of physics what is the origin of the exclusion principle and the idea of fermions and so on. But putting that aside, at that time, it was known that you would kind of, if you had a bunch of energy levels for electrons, you could like fill them up, just as you do in chemistry with shells for electrons in atoms and so on. You could fill them up. And at that point, you would, and so what Dirac imagined was that there was this sea of electron energy levels that were all negative energy, and you filled them all up, but you could have a hole in that sea of negative energy electrons. And that the question is, what would that hole be like? And you realize that hole would be like an anti-electron, be like something with a charge that was +1 instead of the -1 charge of the electron, but it would have positive mass. And so he kind of said, well, there should be this thing, the anti-electron, the positron, antimatter. So it was something that came out of, in a sense, the mathematical setup and elegance of what was going on, that there should be antiparticles. So then people wondered, well, are there actually antiparticles? That the main place to see particles at that time was cosmic rays. There's a flux of particles, mostly from the lowish energy ones are from the sun. There are much higher energy ones from much further away, but they hit the upper atmosphere of the Earth, and mostly it's protons. Mostly the protons interact in the upper levels of the atmosphere, and by the time you're at sea level, it's mostly muons. But people had taken emulsion stacks onto mountains. They were, particularly there was a group in Bristol in England, was doing this a lot, where they would have, so what was an emulsion stack? At the time, okay, you have a photographic plate that is a photographic emulsion. It's it has the feature that when a photon of light hits the silver bromide molecule, the silver gets ejected, and that silver is what you can develop to then show, oh, that's a black part on the film, so to speak. And so the idea was that a photon coming through, actually any particle, any energetic particle that might hit that molecule would eject the silver atom and produce something which was as if light had fallen on that part of the photographic plate. But the idea was to have an emulsion stack. We just had a big chunk of this kind of emulsion, silver bromide or whatever else. And you would end up, if a particle went through, the particle would be sort of ejecting silver atoms all the way through. So you get this whole track where the particle would go through. And what people would do is they take this emulsion stack, they would take it on a mountain, they would have all these cosmic rays go through it, then they would take it apart, and people would painstakingly go through with a microscope and look for little lines of tracks where particles would go through. I might say just a few sort of more personal things about this. I mean, Paul Dirac was, I never met Paul Dirac. I could easily have met him, but I didn't, unfortunately. My friend Richard Feynman certainly did meet him. He always described Paul Dirac as monosyllabic. He said that he just would barely ever say anything. And I gather that Paul Dirac spent most of his career in Cambridge, England, and finally, at sort of the then mandatory retirement age of probably 60 or something, he moved to Florida and apparently became a much more social kind of character there. And somehow the Cambridge atmosphere had caused him to be the one to be in this very monosyllabic kind of mode of sort of almost a very closed kind of answering questions only with one word and so on. I think that Dirac was a very kind of a mathematical thinker, much more mathematical and much more sort of cleanly mathematical than most of the physicists of the time. and he wrote a book. It was a well-known book about principles of quantum mechanics, which introduced many of the notations that we use in quantum mechanics, the bra and ket notation, kind of a cute little thing that's the angle bracket one way and angle bracket the other way. And Dirac called that a bra and a ket, because the whole thing would be a bracket with a C in the middle, but the left-hand side was a BRA and the right-hand side was a KET. So in any case, then, well, emulsion stacks. When I was a student in Oxford in the 1976, 1977 type time frame, it was still the case that there would be this area where people would be going through these, actually by that time it was bubble chamber pictures, but I think they may also have had some emulsion pictures at that time, looking for particle tracks. And they would have a whole setup. They'd project an image of the thing on a big table, and they would have rulers and things. They'd be measuring stuff, and it's like, oh yeah, we saw there's a lambda particle there. It's an inch long track from a lambda particle, or there's a this and a that, and then recording what they saw. And that was kind of still a thing. People were experimenting at that time with various kind of image processing algorithms, and so on, but it was still very much a manual activity of people actually going through and doing this kind of manual reading of emulsions and by that time bubble chamber pictures. But anyway, back in the 1930s, the thing people started looking for these looking for the source of high energy particles was cosmic rays. And people looked for people looked to see what kinds of particles would be produced. Was it always protons? Was it other things? And I think Carl Anderson was the person who discovered the positron. It was kind of three things were discovered roughly at the same time: the muon, the pion, and the positron. There'd been a prediction, I guess, 1930, when was it, 36-ish, something like that. Hideki Yukawa in Japan had been working on the question of how nuclei are held together, and had come up with this idea of pion exchange, that there was a particle about 1/10 the mass of the proton that would be being exchanged back and forth between protons in the nucleus of atoms, and that was the sort of a carrier particle for the strong nuclear force. And people kind of wanted to look for that and started looking for it in cosmic rays. They thought they found it, but they actually had found the muon, which is a particle where nobody knows why it exists. Just like an electron, but 206 roughly times heavier than the electron. And it's sort of a big mystery that maybe we'll have a chance to clear up as we probe more into our fundamental theory of physics, why the muon and the thing called the tau lepton, which is another thing just like a heavy electron, exists. But that was the thing that got discovered first, then the pion got discovered, and somewhere in the middle of that, the positron got discovered as an actual particle that, as an actual example of antimatter. And the antiproton got discovered somewhat after that time. I think that required, I'm trying to remember whether that was discovered in cosmic rays, whether that was discovered in early particle accelerators. See, what happened with particle accelerators is that you are basically going to use electromagnetic forces to make particles go very fast. The initial way of doing that was in a cyclotron, a circular device where you would have these kind of electromagnetic waves that would like push particles to go faster around the circle. That was something that was developed, I think, as a result of radar technology that had developed in World War II, where the concept of a radar tube, the idea of being able to control electromagnetic radiation, to have a cavity where you could excite certain modes of the electromagnetic field and then shoot them out in some direction for radar. Those kinds of amplifiers and things like klystrons and so on were, I'm trying to remember all this history. That was a thing that had been, it was kind of the first big sort of technical thing that in Silicon Valley, Varian Associates was a microwave company that came out just after World War II, I think. But somehow Lawrence Berkeley Lab, which was kind of sort of there were many spin-offs from the Manhattan Project, and many kinds of additional pieces of big physics that got started as a result of that. And one of the main beneficiaries was this idea of, okay, now we understand something about nuclear physics, let's go on and try and understand subnuclear physics. That was what particle physics was originally called, was subnuclear. People talked about subnuclear particles and so on, and particles that were sort of beyond the level of a whole nucleus, what could exist in a nucleus. And the first particle accelerators were built in the 1940s, and that was kind of when a whole bunch of other particles started to get discovered. In the 1950s, well, there'd been a sequence of particles discovered. Everyone had a discovery story. I think the lambda particle, the thing that's kind of like a proton, but eventually was the first strange particle where the proton's mass is 938 million electron volts, and the lambda particle has a mass of about 1115 million electron volts. Those are, for somebody like me who was a particle physics enthusiast when they were a kid, these are famous numbers, so to speak. And then there were other particles discovered, the sigma particles, the 1385 MeV, if I remember correctly. Then the so-called cascade hyperons, which are called cascade hyperons because they decay into sigma particles, and the sigma particles decay into protons. And then one of the things that was sort of a question was, okay, there's this whole zoo of particles that were being discovered, particularly in the late 1950s, early 1960s. Sort of how did this all fit together? And there were two main things that came out of that. One was the thing called Reggie theory, and another was the so-called eightfold way and the quark model. And I think that the thing that, the idea of Reggie trajectories had to do with, well, you would have a particle that had a certain spin like 0, another one with spin 1, another one with spin 2. There would be this whole series of particles that were of increasing spins, and they would be a series from the pion with a mass of 134 MeV to the rho particle with a mass of 770 MeV to the F particle, the rho particle spin 1, to the F particle with a mass of 1270 MeV, at least it used to. I think it may have moved since then, moved as in the experiments got better. And that was a spin 2 particle. And you could kind of plot these lines, whereas as you increase the spin of the particle, the mass would be correspondingly increased. And that was sort of identified as these kind of flights of particles. And the idea, due to Tullio Reggi, and again, somebody I unfortunately never met, was kind of a creative idea of, usually the spin of a particle was thought in basic quantum mechanics to be an integer or half integer. But he said, well, what if it's a complex number? What if it's an arbitrary complex number? Can we think about kind of what this continuous thing as a function of complex angular momentum would be like? And that thinking eventually led to string theory. That was kind of the mathematical underpinning of string theory. But so that was one branch, was kind of the Reggie trajectories idea for these flights of particles. The other branch had to do with understanding why there were protons and lambda particles and sigma particles and psi particles and so on. And that was what led to the quark model, the idea that you could actually sort of break those particles down into subcomponents. It's a little bit like what people like Dalton had done in the 1800s, thinking about atoms and kinds of chemical elements, of thinking, could you, well, first of all, breaking down molecules into constituent atoms and saying they're made from a discrete set of elements, and then later thinking about, well, these chemical elements, what is different between these chemical elements? Oh, eventually, and this became clear in the early 1900s, eventually it's like, Mendeleev had organized the chemical elements in this kind of empirical way into the periodic table and had sort of assigned numbers to these things and so on. And it became clear that what those numbers corresponded to was the numbers of protons and electrons in the atoms of these particular elements. But so sort of that was being retried for particle physics of, could you, by the time you had, there was the thing called the particle data table, was one of my favorite books when I was a kid, the little kind of pocket, very convenient kind of a pocket guide to the particles of our universe, so to speak. And it started off with a a guy called, what's his first name? Rosenfeld was his last name, often called the Rosenfeld tables. I think Rosenfeld went off to go into the electric power industry at some point. But in the early days in the 1950s, this was the thing. I think it's still maintained at Lawrence Berkeley Lab. The particle data group maintains the particle data table. It was from Berkeley and CERN, I think. But anyway, when I was a kid, I used to get these things. I certainly had the 1973 edition. That must have been when I was 13 or so, of the particle data table. There's a very convenient, carried around everywhere little booklet. That little booklet had started off as a kind of one sheet of paper of these tables, but as more and more particles got discovered, there were eventually hundreds of particles, and the question was how could one explain all of these? And sort of the first big break in this was due to Murray Gell-Mann in 1955-ish, inventing this idea of what he called strangeness. And the notion was there were particles and they had electric charges and et cetera, but maybe there was another quantum number, another kind of thing like electric charge that would be characteristic of particles. And for example, the aforementioned lambda particle might have a strangeness, and that would be the thing that would distinguish it from just being a pure proton. And so this idea of strangeness, and there were a lot of phenomena. There was a thing called associated production, where in a nuclear strong interaction, you would only get a strange particle and an anti-strange particle produced together. You couldn't get a single strange particle produced, but then the weak interaction could produce single strange particles. So the weak interaction was strangeness violating and the strong interaction was not. And this was kind of the idea of this strangeness quantum number that was assigned to certain particles. And so then the question really was, how did that, could you then do things like, where did this strangeness idea come from? What was the underlying thing that led some particles to have different strangeness than others and so on? Well, I don't know the full history of this, and I know the people involved, and I still don't know the full history. The Murray Gell-Mann, this is 1963, I think, I knew Murray Gell-Mann quite well. He was, by the time, I mean, I first knew him probably first talked to him in 1976. So quite a few years after the time we're talking about here. But he was, I think, always somebody who liked to have, he's very erudite scientist in many ways. He liked to learn human languages and things like that. He also liked to learn kind of mathematical techniques. And one of the mathematical techniques that he was kind of keen on was group theory. And so he kind of tried to take the sort of idea of strangeness and wrap around it a bunch of things about the theory of Lie groups and a lot of other sort of elaborate mathematical theories. And out of that came kind of a notion that, oh, there must be some sort of collection of particles that were somehow related by some kind of rotation, not in physical space, but in this abstract SU3 sort of strangeness-ish space. Would now be called sort of flavor space. But anyway, so he had this idea. Meanwhile, there was a person who was then a graduate student, somebody I've known quite well for many years, named George Zweig, who was a graduate student at Caltech, who I think did something much less highfalutin, so to speak. Just looked at all these particles and said, if you did the same kind of thing that had been done, you know, for chemistry, for nuclear physics, of just saying, how would you, if you just said, you know, if there were these components that were inside particles, what kinds of components would have to exist to get the particles we know? And so he called those components ACEs. I don't quite know why, I've never asked him. But he then was, he did that. He was actually by then, I think, visiting CERN, and Murray Gell-Mann, also at Caltech, used this sort of highfalutin group theory stuff, but ended up with sort of this idea about this sort of collection of what particles must exist, and sort of by implication ended up with this notion that, well, you could think about that as the generators of this group would be quarks. Now, what were these quarks? Were they actual particles that you could see, or were they just kind of mathematical concepts? And George Zweig took the point of view that they really were physical particles that you could see. And actually, for many years, when I first knew him in the 1970s, he was very intent on trying to search for kind of the consequences of there just being quarks out there in the world. Now, one of the mysteries was, okay, you say there should be a quark that is a constituent of a proton, but the quark would have to have a charge of 1/3 of a unit of electron charge. And people said, but charge is somehow quantized. We don't quite know why. People still don't know why charge is quantized. Actually, Dirac had an argument for why charge was quantized, would be quantized. If there existed just one magnetic monopole in the universe, charge would have to be quantized. But so far, we don't think any one of those exists. So that argument doesn't really quite work. But so people didn't know why charge was quantized, but it was observed to be quantized. And the idea that there should be a particle with 1/3 integer charge was a very shocking idea. And more than that, people said, but look, we've never seen a particle with 1/3 integer charge. In no particle experiment, particle physics experiment or anything has that ever been seen. And so that was sort of a mysterious thing. And people said, well, maybe if we have a bigger particle accelerator, we'll be able, just like we were able to break nuclei up into their constituent nucleons, protons and neutrons and so on. So similarly, if we hit a proton hard enough, it's just going to shatter into a bunch of quarks. And it had 3 primary quarks that it should be made of. Maybe it'll just sort of shatter into those quarks. But people didn't find that. And so it sort of became quite a mysterious thing. How could quarks exist? What really were they? Were they just mathematical? Were they really things that existed? What was the story behind that? But from sort of the group theory angle of, well, if you just thought about these rotations and these quarks were generators of rotations and so on and so on and so on, whether they exist as physical things or not, then the implication was that you could get a that there was something that had to be true. There had to be another particle. There was the thing called, there were these different groups of particles. There was a thing called the octet of 8 particles, needless to say. And there was a thing called the decuplet of 10 particles. But only 9 of those 10 particles were known. There was one missing, a strangeness -3 particle that was at the, if you drew out the way that these so-called multiplets, you could draw them out as a function of well, a thing called isospin and hypercharge, which is like strangeness. And you could draw it out, and there would be, at the peak of this triangle, there was something missing. And so Murray-Gell-Mann made this prediction that there should be a particle there. He called it the omega minus, capital Omega minus. And it should have roughly a mass, I think 1675 MeV, something like that, because you could work out, there was sort of a mass formula that, which in the end comes out about because the strange quark has a different mass from the other quarks. And so that leads to different masses of particles that contain strange quarks. The omega minus, as we now know, is a particle made from 3 strange quarks. Anyway, in 1965, maybe 6, sometime around then, the omega minus was discovered in a bubble chamber at Brookhaven National Lab on Long Island in New York by a guy called Nick Samios, I think. And you see it as a little track in this. There's an omega minus, and it decays into a psi particle, a cascade hyperon, which then decays into a lambda particle or a sigma particle, which then decays into a proton. And you see all that happening in this bubble chamber picture, just little tracks. And every time there's most of the tracks are straight, and then they maybe break up in 2. And then every so often there's this curlicue kind of spirally track. That's an electron kind of spiraling to rest as it keeps on hitting other atoms in the bubble chamber. So in any case, that was a big triumph. It's always exciting when a theory makes a kind of a slightly unexpected prediction. People go out and look for it, and then they find it and nail it. I'm kind of hoping that's what's going to happen with our fundamental theory of physics. We've got a number of leads on possible kinds of things, but it's always usually a lot of work to go from the fundamental theory to an actual prediction where somebody can go, measure something with a particle accelerator or a telescope or some such other thing. But anyway, the omega minus was sort of big triumph, and it's like, yes, this quark theory is right. Murray had called it the 8-fold way because it had this octet, this 8 particle combination, and that was sort of in in reference to Buddhas and Buddhism and the Eightfold Way there. I think that was a kind of a piece of erudition that I don't think there was much Buddhist about the whole thing. Another person who'd been involved in that was a person who worked with Murray named Yuval Ne'eman, who I met only a couple of times, who was a high-ranking politician in Israel, actually, who had been very much involved in this Eightfold Way creation in the early 1960s. But in any case, the thing that then happened with respect to quarks is George Zweig was convinced that there would be physical quarks somewhere, that somewhere in some chemical process, somewhere in the formation of the Earth, somewhere in some high-energy cosmic ray, somewhere there would be quarks. And he spent a lot of time doing rather interesting work on sort of the chemistry of 1/3 integer charged particles. Where would they go? You know, would they wind up in seawater? Would they wind up in this place and that place? But no quark was ever found. No free quark was ever found. And then QCD, quantum chromodynamics, came along, and people got this idea that maybe quarks were confined. Maybe there were forces, these QCD gluon exchange forces, that between quarks, and that were just keeping it confined, so that actually what happens is, well, maybe I shouldn't go into this in more detail, but when you try and pull two quarks apart, if you have electrical forces between things, the kind of lines of electric force kind of go out like a hedgehog, so to speak, from each particle, and the number of lines of electric force that intersect when the particles get further apart get smaller and smaller, and that's why you have the inverse square law for electrical attraction. But in the case of QCD, because gluons interact with themselves in a way that photons don't, those lines of sort of flux, of QCD flux, of color charge flux, those lines of flux attract each other. And so instead of having something where it looks kind of like a hedgehog of lines of flux, you have something where all those lines of flux get pulled together into this kind of string between the quarks. And so as you pull the quarks further apart, that sort of string gets tighter and tighter. There's more flux there, more energy has to be expended. That's kind of the qualitative picture for why quarks are confined. Now, we don't actually know from a mathematical point of view, nobody's proved that in QCD quarks have to be confined. It's a difficult problem in quantum field theory that has been sitting unsolved for the last, well, since 1973 when QCD was developed. But in any case, the other thing that happened, this must have been 1970, I think, was that people were just kicking protons really hard with electrons, particularly at the Stanford Linear Accelerator Center. It was possible that it was accelerating electrons to high energies and just shooting them into a target with, I don't know, it had protons in it. And they would find that most of the time, the electrons would just go straight, it wouldn't be like they were hitting a hard thing. They would just kind of keep going in the same direction. It's kind of like when Rutherford was doing Rutherford scattering back in the early 1900s, most of the time when he would kind of shoot an alpha particle near an atom or something, most of the time would just keep going straight through, because most of an atom is empty space. And so most of the time, the thing that was being shot at the atom would just go through the empty space and just keep going. But occasionally what Rutherford found was, well, occasionally it hit a hard bit, and that was the nucleus, which is 100,000th of the radius of an atom. It would hit the hard bit in the middle and bounce back sort of the way it came, or closer to the way it came. Well, the same exact thing was found with electrons in protons, that most of the time they would just sort of go straight through, but just sometimes they would hit something that seemed like a hard bit and they would kind of bounce back. And this question of, well, how do you characterize that process? There was you could kind of characterize the momentum transfer, which was sort of how much momentum was transferred from the potential hard bit to the thing that was coming in, and so on. And there was a whole whole story of that. A person called Jim Bjorkane who was at SLAC at Stanford was a big figure in that whole story. But then the person who really pushed this in the end was Dick Feynman, who came up with this thing he called the parton model. And the parton model was kind of a nose thumb at Murray-Gell-Mann, because he was saying, well, there are hard bits inside protons, and we're going to call them partons. Now, people strongly suspected that if there were hard bits inside protons, they were actually quarks. But that wasn't known for sure. And Dick Feynman kind of decided he wasn't going to give Murray sort of the benefit of the doubt. These are partons, they may or may not be quarks. And I think Murray was actually was very nervous about the idea that quarks had some physical existence, because people were sort of telling him, oh, you know, they're always confined. How can you consider them as particles? That's not really a particle. Our definitions of particlehood don't cover things that are always confined. So, you know, it's just a mathematical construct. I think he was perfectly okay having them be thought of as things that were kind of just mathematical and didn't have some instantiation where you could shoot an electron at them and it would bounce back. But I remember Dick Feynman telling me, he gave a talk, I think 1971, maybe sometime like that, a little bit before when I knew him, at Stanford, where he sort of introduced this parton model. And he told me he'd kind of stayed up all night the night before. He'd got all this experimental data, and he was trying to figure out, how could you explain this data? Oh, you can explain it if there were these hard bits inside protons. And then he kind of gave this talk, which was this kind of famous talk of kind of just sort of the outline of how this parton model would work. Well, I asked him, you know, did you actually, you know, there's certain intuition about how things would work with hard bits inside protons, et cetera, et cetera, et cetera. It's like, how did you know that these pieces of intuition will be right and other pieces of intuition wouldn't come and sort of bite you with different effects? Well, he said, well, of course, he worked out some whole toy model with quantum field theory. But he didn't tell anybody about that. This was very typical Dick Feynman. You know, he'd do a lot of very elaborate calculation, but he thought that was kind of the easy part. It wasn't easy for other people, but it was easy for him. And so he kind of threw that away and instead gave this sort of very beautiful, intuitive description of kind of a little bit like the one I've tried to give you here, about kind of hard bits and protons and so on, and what consequences that would have from experiments. And for years afterwards, people were like, but how does this work in terms of quantum field theory? People were trying to figure this out. But that was something that Dick Feynman had already figured out before he even first presented this idea. But I think I'm not sure he ever published any of that stuff. By the time I knew him, this 1976, 77, I guess, maybe even 78. He was actually pretty interested in sort of looking at what were then called parton showers. Maybe actually I called them that. I'm not sure if that might even be my name for them. They were things which in a high energy collision, you would get sometimes a whole, what would now be called jet of particles produced in some direction in a high energy collision. And there was sort of what happens when you hit a quark hard and it kind of gets pushed out of the proton it was in, and it goes off in some direction, but it can't be separated as a quark. So it has to kind of drag other particles. It has to produce other particles off in that direction. And that's what leads to these jets of particles, which I spent a bunch of time studying. And Dick Feynman was also interested in studying back in the late 1970s, much to the chagrin of people like Murray Gell-Mann, who was saying, because it was kind of a messy business and it involved, you know, what were then Fortran programs, things like that, of actually working out, you know, oh, there were going to be 50 particles produced, you know, what's the chance that there'd be a bunch of pions and this and that and the other. It was kind of messy. And Murray was always like, you know, saying to Dick Feynman, you know, why are you working on all this messy stuff? And Murray would say to me, why are you working on this messy stuff? You know, it's just very inelegant and so on. It was kind of, I think in those days, it was sort of methodologically a bit different because it involved a bunch of computer simulation, Monte Carlo simulation of sort of, let's generate a whole bunch of events at random, particle events at random, and then make sort of aggregate curves of what the typical behavior is. That was something which was a little bit of I would say, I mean, that the Monte Carlo method had been invented during World War II for studying neutron effects in nuclear reactions, but this sort of application of it to particle physics, I think I'm kind of thinking, I think that was kind of new at the time. It was sort of an obvious thing to do. I have to say, to my great chagrin, I was quite at that point already quite decently sophisticated in kind of theory of computation and sort of what would later be called software engineering and so on. But I didn't write the actual code that we used to do a bunch of these simulations of particle jets and so on. And pretty arbitrary set of like numbers for a pion is a 17 or something, a kaon is an 18, because these things all had to be translated into Fortran code, because that was the language that was being used at that time. And I do believe that that crazy set of numbers that were sort of very arbitrarily assigned have ended up becoming the standard that is still used today in jet simulation programs to compute, events at the LHC and things like this. And it's a little bit embarrassing in a sense that I didn't get more involved in that and kind of try and use what I've spent kind of a lifetime now honing of sort of software design, and making sure that, oh, there's a very systematic way to number these things, et cetera, et cetera, et cetera. Anyway, sorry about that. Well, let's see. That was a very long answer to that question. Wow, let me see. There's some questions here. All right, there's a few simple ones here which maybe I can talk about. Aaron asks, how did I first meet Nassim Taleb? And why do I think he was able to take a computational approach to finance instead of reasoning by analogy? It's an interesting question. I first met him, I remember, it was I met him in the lobby of some hotel in New York City, long before he was kind of started writing books and things like that. He was a trader at the time, and I met him through a friend of mine who's in the quantitative finance business. And he was, as he has always been, a colorful character. And I remember him making all sorts of wonderfully kind of snarky and unexpected comments about all sorts of things. It must have been 20 years ago, something like that, roughly, sometime like that. And I don't really know. I think Nassim has used sort of mathematical computation a lot, usually using Wolfram language and Mathematica and so on. And I'm not sure he's been as much into the kind of heavy duty computation as most of the quantitative, the big quantitative hedge fund folks, the Renaissance, the D.E. Shaw and company, the now Two Sigma, things like this. These are all outfits that have, in different ways, kind of found ways to use computation to kind of predict things about the market and so on. I mean, it always used to be the case, all these places are, I'm happy to say, big users of our technology. It's one of these things where everybody has their secret methods for beating the market, and I don't know what they are, so I can't tell you and spill any secrets. But my impression is that everybody has sort of different, one firm will be using regression analysis. It's just all a giant regression analysis. Another firm will be using, computational geometry. It's all about that kind of thing. Another firm will be using some other kind of technique. People kept on saying machine learning is going to take over. I don't think that's quite happened. I mean, people have been using people have used neural nets for a long time in finance. People had these periods when it was like, it's going to be chaos theory, it's going to be fractals, it's going to be transfinite numbers. That was a weird one associated with high frequency trading. But I don't think I think it's one of these things where it's a continual kind of race, and sort of any technique that gets you a little advantage is interesting. But in any case, I think Nassim has been much more on the thinking about kind of tales of distributions in a way that sort of mixes mathematical ideas with kind of everyday intuitional ideas, and sort of a mixture, interesting mixture of, usually investing is divided into this kind of fundamentals versus more technical, where fundamentals is kind of like, I actually want to meet the people who run that company, and I'm actually going to have a theory about what the company does, versus the more technical side, which is, I'm looking at all these numbers and all I know about that company is its ticker symbol. I haven't a clue what it actually does. and I don't really care. All I know is that it's, its kurtosis of its, its volatility of its stock price has this, and it's got a tail that does that, and so on. And the fact that it makes bricks for a living is absolutely irrelevant. All I care about is the fact that it has this kind of volatility every spring or something. And so I think that those are, I think Nassim is sort of in the middle of those two, with a kind of intuition informed by mathematical ideas, but I think a quite fundamentals approach to thinking about economics and the market and so on. All right, maybe one more thing, and then I should wrap up here. Well, there's a question here from Aaron. How does the log4 shell vulnerability compare to other historically significant web vulnerabilities? Does the internet tend to change course after large vulnerabilities? I would say the basic answer to, well, okay, so the history of internet vulnerabilities is an interesting one. Again, it was something people kind of, okay, I remember this must have been 1970, maybe, when I was pretty young, hearing about some of the first computer exploits. And I think they were done at MIT. And I think the idea was the following. You got a password screen. It said, type in your password. That was passwords were already an idea then. And probably it was a password screen. I'm thinking it might have been some kind of other input field. But then the basic notion was, well, what if you just type a bunch of garbage in there? What if you just keep typing and you keep, putting in characters, and it way overflows the expected length of that input field? And turns out that kind of vulnerability, they're still with us today. People still make this mistake today. They'll have something where you expect a certain amount of data to be put into this field, and actually if you stuff more data in there, some of the data will get stored in memory in a place where it shouldn't have been stored. It'll overwrite something else, and pretty soon the program will have escaped and started doing things. I think the thing to understand about computer security in general is the following thing. Insofar, the goal in computer security, in modern computer security, is get a program to do something it wasn't intended to do, and eventually get that program to go and sort of reach into the computer and start grabbing things that you want, or controlling the computer, or whatever else. But what you are trying to do then is take a program and make it do something that it wasn't intended to do. Well, big sort of idea of computation is this idea of universal computation, that there are programs, systems, languages, whatever, you can take a universal program and you can make it do anything you want. That's what it means to be a universal program, a universal computer, universal language, whatever, it's all the same kind of idea. So the question is, as you go and type extra crud into the buffer of of some program or something, can you somehow manage to poke that program in such a way that it becomes essentially a universal program, or make use of the fact that it already is a universal program, but you're now feeding it a different program to run as its piece of software, so to speak. And then that allows you to go start taking over the rest of the computer. So the problem is, as everybody wants everything to be smart, everything has to be a universal computer. Your typical firewall that's trying to throw out bad packets that are coming into your computer system, that's definitely a universal computer. First of all, it's running on a general purpose computer, but second of all, even at a software level, it's got all kinds of sophisticated things inside it. It's one of the things that's come out of my science work, is this principle of computational equivalence that kind of suggests that even systems with very simple rules can be capable of arbitrarily sophisticated computation, in particular universal computation. And that's why it's really unsurprising when people say, oh, by looking at CSS on the web, oh, you can make a universal computer out of that. Oh, if you look at this aspect of something on a blockchain, you can make a universal computer out of that. This doesn't surprise me at this point. You can make a universal computer even out of extremely simple components. And so that's kind of the thing that one tries to do in computer security exploits, is can one sort of reach out of what the program was supposed to do and into this kind of universal zone, and then use that to take over a computer? Well, I would say that the earliest kind of internet exploits. So there are lots of exploits on computers directly at the computer, so to speak. And people, the earliest internet exploit that I think is known about is the Morris worm, due to Robert Morris. I remember meeting, well, I was a consultant at Bell Labs for a while in the early 1980s. And Robert Morris's dad was a computer security researcher, actually, at Bell Labs. I remember meeting the young Robert Morris as teenager at some party at that time. But anyway, subsequently, this must have been, when was this? This was late 1980s. Robert Morris was, I think, a student at Cornell, and somehow managed to write a worm, a program that would go and infect go out on the internet, infect computers, and replicate itself, and then spread to other computers and so on. And so there was this terrible moment, I forget when it was, it must have been 88, 89, something like that, when this worm was spreading over the internet. It was sort of the first time a lot of people had heard of, well, any of these issues of computer security and so on. And we were, at that time, we had been sort of early to the internet. We were, we had gotten our domain, 140.177. That's our network address, which we've had forever. But one of the things that I was, for some reason, aware of, I can't even remember why I was aware of this, the whole issue of, that the internet might be sort of a vector for computer security issues. And so one of the things I did was a question of what would be the gateway computer that we would put that would connect from our computer network out to the outside internet. And at that time, we were making what was then Mathematica run on all kinds of different computers. So we had computers arriving from all over the world, of people, making deals with us to port Mathematica to run on their particular kind of computer. And one of the slightly exotic computers was Sony had made a workstation computer. It's called the Sony News computer. I don't know, the news it was spelt with a lowercase e, and the other ones were capitals. I don't exactly know what it stood for, but in any case, it was a somewhat unusual computer, let's say, and its operating system was in Japanese. And I, for some reason, had realized that we could connect to the internet with any gateway computer we wanted. And so we happened to use that computer to connect to the internet, because it was a computer we had around. And that turned out to be a really good move, because in those days, and I think it's still true, these different kinds of worms and viruses and things, they have to be compiled for different kinds of computers. And they've been compiled at that time for various kinds of VAXs and Sun workstations and so on, but nobody had compiled a version. The worm had not been compiled for that Sony computer. And so when it got to our connection to the internet, it was like, I don't know what to do here. So it just ignored it. And so we were just fine, and our computers were not taken down by that thing. But the thing that is the case, people have there's a whole kind of strange underworld of people trying to find vulnerabilities in software. And there've been all sorts of efforts to take, for example, people have sometimes said, oh, open source software is going to be better because everybody can find the vulnerabilities. Well, the problem with that is both everybody can find the vulnerabilities and everybody can find the vulnerabilities. So and there's a regular stream of vulnerabilities found either by governments or by independent contractors or by people who are essentially entrepreneurs finding zero-day exploits that have never been done before, that can be sold. I don't know what the going rate for one is. It used to be $10 million. I don't know what it is these days. Was sort of the going rate for a zero-day exploit in some known operating system and so on. And so that tends to be somebody finds these. I don't know how systematically they're found these days. I mean, I certainly know that for a while I was kind of avoiding various kinds of methodologies that I think could probably systematically find those things that come out of kind of some of the science that I've done on sort of exploring the computational universe of possible programs. But I think probably by now the sophistication of efforts to find those vulnerabilities have exceeded the things that I had imagined for doing that. But that's sort of the typical process, is somebody will find these by some kind of, oh, you take something, you fuzz around the input, you look at this, you look at that, and then what happens to the exploit is a whole different story of whether it gets just reported to the public, whether it gets used by some military, whether it gets used by some shady outfit, to do something terrible and so on. It's it happens, but I don't think. What I've seen is there are sometimes like the Morris worm where people sort of woke up to the idea of security of networks and so on. I don't think that there's sort of huge effects from, it doesn't feel like, it feels like there are things like bad things that happen in the world, plane crashes, things, crazy things people do that, once somebody did that, then there's all kinds of protections that get set up, and everybody, has to take their shoes off going through an airport security line or something like this. Once that sort of hack was done once. I would say that most of the time in computer security exploits, it's like there's a piece of software, it gets patched, it's like, okay, we're good now. There's a little bit of kind of paying attention to the supply chain of software, but I would say that there is much, from my observation as something of an outsider, there is much less systemic, oh my gosh, this happened. I mean, one common thing is people who use random pieces of open source software where it's like, some random person put that random JavaScript library in somewhere and it's being called by this, it's being called by that, it's being called by that. And oh, well, somebody out there in the crowd, the amazing crowd, makes a change. And by golly, this giant chain of, half the JavaScript installations in the world suddenly get this change. And oh, whoops, there was a bug in this change. Whole thing comes crashing down. You would think that by the time that it happened a few times, that people would be kind of wise to that issue. But I feel like it hasn't as much been the case. I mean, it's often an excuse to execute one of the more common bait and switch techniques for open source software of, yes, there's a version that's out there in the world, but it isn't really secure, but we'll get you a much better, securer one and so on. But I think it's, I have to say there are places in, in medicine, in, airplane disasters, in military things where, people study the problems that occurred from the distant past, and people are still studying battles that were fought in in ancient Greek times and so on for like well, don't make that mistake or something when you fight a battle today or whatever. It's not my impression that as much of that is going on in computer security as one might think, and that there are more kind of, well, we patched that one, we'll be okay, let's go on until the next one happens. Not sure, but that's at least my impression from the outside. All right, I think we need to wrap up here for today, but thank you for some interesting questions. I see some more saved up, which we can address another time. So thanks very much.